Hi, thank you for joining Human Capital Gains. Today we are joined by Chou. Tim, I'm going to get into it a little bit. I'm going to ask the question that might be on everybody's mind. You've had a career that most people would kind of consider complete, right? You started leading Oracle's cloud business. You're a professor at Stanford. So, what's the specific moment or maybe the specific story that made you realize you couldn't really stay retired and wanted to venture into this new business?
Yeah, well, first of all, thanks for having me on your podcast. I'll tell it to you in this way. I was fortunate, got to retire early, so I started teaching class at Stanford, and being a advisor, counselor, whatever, mentor. But I have to tell you, after about 10 years of doing that, I was kind of chafing at the bits, like, give me the wheel again. I don't want to tell you what you should do. I'm just going to do it, right? I had that instinct to want to do that. Fortunately, let's call it 10 years ago, I teach this class and I had a strange student show up who had an MD, an MPH, an MBA. He's chief of pediatric cardiology at the Children's Hospital of Orange County. His name's Anthony Chang. And so I like to say Anthony adopted me. I had never spent any time in healthcare. And I learned things like, oh, you're kidding me. You guys still use CD-ROMs. And of course, the usual retort I get is, yeah, it's better than fax. It's like, okay, I agree. And then way at the other end of the spectrum, as I think everybody realizes today, if you're going to go build AI applications, you have to have access to large quantities of data, diverse data. Otherwise, you can't build accurate algorithms. So right around COVID timeframe, I'm sitting around thinking, watch Netflix all day or maybe do something useful. And so I grabbed a group of engineers and we gave ourselves a mission to reduce healthcare inequity, lower cost, improve outcomes for children locally, rurally, and globally. How are we going to do this? By creating real-time, privacy-preserving AI applications based on access to data in all 1 million healthcare machines in all 500 children's hospitals in the world. It's what we call the Pediatric Moonshot, which we think we named correctly. And I think it was just, confluence of events, my feeling about, wanting to hold the wheel again, the realization that I knew how the technology would have to work here, that fundamentally centralized cloud computing, I was in the middle of that, would never work in healthcare and life science. We can't just push all the data into a big data center in Louisiana and put a terawatt of power out back. The data sizes are much larger. Ultrasounds are a terabyte apiece. Security requirements much tougher. Privacy much stricter. So we basically said, well, rather than it's kind of computer science 101, rather than move the data to the application, move the application to the data. So engineering a distributed AI cloud infrastructure really became just a very natural next step or a next evolution of what should happen in cloud computing.
So like my proud experiments with sourdough starters during COVID, just like I feel really inadequate now considering what you did with your free time. So let's there's like a million questions I want to ask you, Tim. We had a couple really good conversations, but just maybe to add a little bit of color to when you talk about like instead of moving, the data to the cloud, like, moving, that sort of interplay, because privacy in healthcare is like a really, really big topic. Like everyone's super sensitive to it. So can you maybe unpack that a little bit? So for listeners that aren't super familiar with maybe a good analogy or a good example so they can kind of get their heads around it a little better.
Yeah. So maybe let me start with making a point remember I said the mission was 1 million healthcare machines in all 500 children's hospitals in the world, because we knew that there was way more data sitting in the ultrasound, the blood analyzer, the gene sequencer, et cetera, than in the doctor's notes, although we're cracking through that problem as well. So the question became, well, and I'll just pick on ultrasounds since we started in cardiology. The question becomes, well, how do I get a hold of the ultrasound data in a privacy preserving and secure way? Because if I could do that, then great, I can compute on it. I could transfer the image. I could infer on it that there's a congenital heart defect, or, which is really the hard part of the problem, how do I learn on large data in a distributed world. Now, conveniently enough, a lot of your listeners, I'm sure, have their iPhones. Apple had to crack this similar problem, which is, how do I make Siri be more accurate? Well, it could say, well, I'm going to take Marco and Gary and Tim's last voice print and send it to the Apple cloud and learn on it. But of course, there's privacy implications to that. And then who's going to pay for the network bandwidth to ship it there? So they ended up building what some people will call federated or swarm or distributed learning, meaning they're learning on your device and only sharing what they learn with what is referred to as an aggregation server. So we just said, well, this same idea could work for medical imaging or for EKGs or for blood analysis, et cetera. We've actually done experiments that prove this out. There's 2 teams in Germany that have done work in this space, which is why the step we're in right now is really, we want to build a privacy preserving AI supercomputer for children's medicine, because you can't do AI without the data. So this supercomputer will span 32 sites, have all imaging machine data available in real time, all PACS, all EMR data, roughly 3,000 servers, roughly 2,000 terabytes of data flowing through it annually, and roughly 6 million what we call patient digital twins, on which now we can take, we're tracking right now over 175 research applications where a doctor at, Stanford or Mount Sinai or UCL has gotten a hold of 1,000 ultrasounds or 500 MRIs or 1,000 X-rays and built a early detection for multiple sclerosis or congenital heart disease or disease progression in a variety of diseases. They publish in Nature magazine a beautiful paper showing their results, but we all know that, the likelihood this is going to run in the wild is very small. The example I use for people is, for those people who've been in San Francisco lately, you've probably played around and ridden a Waymo. Well, which is pretty cool if you haven't done it. It's a lot of fun. Okay, I always ask people, let's assume you took that Waymo car and put it in London. Do you think it would work?
Right.
And the answer is hell no, right? It was never trained on driving on the wrong side of the road, right?
Yeah.
Right.
And so, because the infrastructure today in healthcare does not allow for pushing it all into one central site, you have to figure out how you're going to do this learning on a distributed basis. Hence, this effort to go build an AI supercomputer for children's medicine to be able to expose these applications to way more training data than they ever could see before.
So one of the things that really interests me in what you're doing, especially like you coming from the outside, a non-healthcare practitioner, having had done a bunch of stuff in healthcare on the administrative side, and we work with healthcare clients. There's a do you get any pushback, right? Like, because you're quote unquote not one of them, and like what are the sort of challenges you're having to navigate, sort of trying to build this sort of new vision of healthcare and like not coming from a healthcare background yourself?
Yeah. I'll tell you that very early on, just to be clear, when we talk about this infrastructure, we literally are putting cloud servers on the network inside the firewall in the clinic or hospital. So let me tell you, the very first conversation we had with IT was followed with NFW. So, we knew going in we were going to get objections on day one, right? And just to close that piece of the story out, because we knew that, we engineered over 30 security and privacy features. One of the core team members has 15 years of privacy law experience. So we knew that going in that objection would exist. But if you take it a little bit broader and not just talk about the IT objection, which, as I said, is fairly easy to handle, it really comes down to something where, I serve as chairman of the Alchemist Accelerator, which is a B2B accelerator. And the conversation I have with every startup is pretty much the same. I said, your challenge in the early going is you have to find early adopters. For those of your listeners who've never read the Crossing the Chasm book that Jeffrey Moore wrote years ago about technology adoption, I heartily recommend it. Less than 100 pages, but he talks a lot about the early adopters of anything they buy the vision. They actually don't buy the product, right? It's the later stage people, which in his nomenclature are Main Street buyers. The Main Street buyer always asks the question, well, who else has done this? And can you show me the ROI? Of course, if you're an early stage company, nobody's done it, or only two people have done it. So I always say, if you meet somebody who asks you that question, how many other people have done this and what's the ROI, you should buy them lunch and move on. Because that's not they're never going to be convinced. You cannot convince a Main Street person. It doesn't matter. So the key, though, is to find the early adopters. And in enterprise software, I say it's 1 in 10. You better have 10 conversations to find one. I think in healthcare, it might be 1 in 25, but it's really progressively building that tribe, which I think at this stage, we have a fairly large tribe of clinicians, CEOs of hospitals who are like, yes, this is where we have to go. And I think it's building the coalition of the willing, has often been said this way. That's really the key. And they will help the next group that will help the next group. And that's how this is going to happen. You will not, there's a whole group of people we will never convince at this stage of the game.
So I think that one group helping the next is a really poignant part of your story too, because, when we've talked about it in the past, you've really kind of like highlighted that staggering shortage of specialists around the world. So how does Moonshot kind of like export the expertise of these world-class clinicians and physicians that you have?
Yeah, I'll just throw a few statistics for people to think about. In the United States, 86% of the rural counties in the United States, which means pretty much all of them, have no pediatric cardiologist whatsoever. We have 3,000 of them in the United States, as what I just explained. They live in the major metros. You go to India, there's 300. You go to Rwanda, there's one guy, right? So, and you could take the other specializations and you could do similar numbers with them. So at the end of the day, kind of the way we're looking at it, it's like, well, what? We're going to build more medical schools and and hospitals and train? No possibility. And then what? Economically incent them to live in some rural area of Montana or whatever? No, it's never going to happen, right? And so when you talk about exporting, which is the way we think about it, the brains of the best people. Just simple example: congenital heart disease. Congenital heart disease affects, most people don't realize this, 1 in 100 babies that are born have a congenital heart defect. A congenital heart defect is an anatomical defect of the heart. As an example, some kids are born with a single ventricle. Crazy, right? Okay. It turns out it is possible prenatal, like fetal ultrasound. It is possible to use ultrasound and detect these anomalies before the baby's born, which is kind of cool, because then if you can recognize it, you could go, well, maybe this baby really ought to be born at Stanford because they can do surgery on it right away. Because one of the conditions is they call it transposition of the great arteries, which is indeed the arteries are flipped around. So the babies are born blue, right? Well, it is knowable. Just to let you think about it, outside the US, it's almost, certain death. It's the number 2 cause of death in children in Mexico. So can I take, if you conceptually think about it, can I take the world's best cardiologist brains and put it inside a computer? Hell yeah, to be able to detect. And there are I mentioned 175 research projects. There are 15 of them around the world in how I do congenital heart defect detection, early ultrasound, EKG, ECG. One of the very interesting things, in fact, I was just, my old office mate, we were first line managers at Tandem Computers together. He reached out the other day and we haven't chatted in a long time. He's retired, moved to Folsom. And so we got on a call, we just chit chatting, and he's I don't know why he went into this conversation, but he goes, I have a congenital heart defect. I went, really? A congenital heart defect that was discovered when he was 40 years old.
Wow.
Yeah. And only recently has there been a drug that could potentially correct the problem that he has. And he's in his late 60s. So It's interesting that congenital heart disease, it spans this entire range from a baby being prenatal, not even born yet, all the way to an old guy. And we have the technology. The the thing about it at the end of the day is you go, we have the technology to do this. This is not, I mean, it may sound rocket science, but it really isn't rocket science to go do this. And so can we put the best brains in neurology, oncology, et cetera, into a computer? Hell yeah. I'll give you another one just so the listener can think about things. There's a condition called focal cortical dysplasia. It's actually a brain lesion, meaning an aberration on your brain. If left untreated, the kid has epileptic seizures. There was a kid in Florida who 2 to 3 times a day would have a seizure. At night, he wakes up screaming. MRI imaged him very early on, didn't see anything. They proceeded to give him all these drugs, some they could afford, some they couldn't. They were getting ready to put in electrical implants into his brain. They re-MRI imaged him, and they now believe he has this condition, which, and I've actually seen the not his MRI images, but I've seen MRI images of focal cortical dysplasia. It looks like a fuzzy dot, almost the same as another fuzzy dot. But that fuzzy dot, if you can find it, you can surgically remove it, and the kid's cured for life. Freaking amazing. Okay. Good news, bad news. Good news, only 25,000 kids a year in the US have this condition. Bad news, how many pediatric neuroradiologists ever see focal cortical dysplasia? On the other hand, if you said, look, if I had every MRI image of every kid in the US or around the world, we could build, it's not that hard to go build a FCD detection algorithm that could run in real time on every MRI imager out there and go, hi, it looks highly likely that this kid has FCD. I mean, this applies to so many different things that you realize that even humans, for a lot of these conditions, they can't be experts because they don't have enough experience.
So how do you sort of navigate? We were having a conversation before we started, right? That culture of medicine, right? Where I always talk about it. I'm probably going to offend a bunch of my friends that are physicians, but it's like back in the day, the science part of medicine was kind of by luck, right? Essentially, like Gary's not feeling well. It's like, okay, I'm going to send him to Tim, who's our village shaman. And Tim is going to find a bunch of roots and make a bunch of ceremonial things. And hopefully Gary gets better. And then we kind of stumble across things. So look at one end, it's like this sort of like mysticism, like divine intervention. And on the very other end, you have people that are like, it's just like the scientific method and it's incredibly rigorous. And it's like, just some complex algorithm of things. And most people I've talked to, they're somewhere in the middle, right? Most practitioners believe in evidence-based medicine and they believe that that's the way to do it. But they also believe that there's something to sort of like the human bedside manner, practical human touch piece of it that's like integral to treating disease or understanding disease. How do you balance that with like this notion of like a distributed AI brain that's going to be, interfacing with patients from a cultural perspective in medicine? Or has that been a challenge?
No, well, I'll say this, yes and no. I mean, the yes, is it a challenge? I mean, we're living in an age right now where there's a group of people who see AI as, Terminator 2, and some of us who see AI as maybe Star Trek 3. So yeah, there's a group of people who, see a Terminator future, and it's hard if you see it that way to acknowledge what this type of technology can do. On the other hand, I'm not going to say that, the human touch is not valuable. I mean, we're a long ass way away. Frankly, even if you watch Star Trek, there's still a chief medical officer, right? So I don't think, this whole idea of, there's no physician. I mean, that's not anywhere near. On the other hand, I'll give you another example of something we're working on over in the world of pharma. They are increasingly building what FDA calls orphan therapeutics. So orphans, by definition, apply to 200,000 people or less. And I'm not talking about pediatrics. I'm talking about across the board. And this is actually, if you look at it, this is the long-term trend. They've been talking about this for years, right? That we're going to get to precision medicine, right? We'll build a drug just for Marco or just for Gary, right? So 200 million is now 200,000. Okay. There's a huge challenge question, which is, how do I find the patient? Right?
Right.
Wait, 200,000 is nothing, right? I'm going to run Super Bowl ads. If you look at what they do today, it is super primitive, right?
Right.
Okay. So what have we introduced? I mentioned very early on the first version, phase 1 of this quote AI supercomputer has going to have 6 million patient digital twins. So what the hell does that mean? So what we're doing is we're saying, and this is a good example of where the human and the computer can be working together. The first thing we're doing is we're basically training a local large language model on the complete medical record. We've started in oncology. Just to give you a sense of this, an oncology medical record could be 3,500 to 7,000 pages of PDF. So you're like, how the hell does a physician go through 3,500 to 7,000 pages? Not possible. This is why, we all colloquially notice that you show up in the doctor's office and they ask you all these questions. You're a better database than them with a PDF document and a search bar, right?
Right.
But in our world, we can train a Marco digital twin on your complete medical record. And now and as I said, we were in oncology. We didn't realize like a oncology nurse in chemotherapy, he or she will spend 15 minutes every session just trying to calculate how much cisplatin the patient was given. Well, this is super simple. You just ask it, how much cisplatin was the patient given, right?
Right.
Which is cool from a productivity point of view. But let's flip over to my conversation about orphan therapeutics. And I'm going to tell you a story around rare kidney diseases. Okay. There's a rare kidney disease called FSGS. It is an orphan therapeutic, less than 200,000 people. So you kind of go, well, okay, I have an answer. I have a drug for FSGS. How do I know the patient has it? Becomes the question, right? So we've engineered what we call disease precise AI agents. It is literally 34 questions, or when we're talking fancy, we call them multimodal biomarkers. It's urinalysis result, blood analysis results, right? So there's a set of questions for which there is a correct answer. Yes, greater than 3. And then if that's answered in the affirmative, then you get a certain number of confidence points that this patient indeed has FSGS. You let the agent run nightly or weekly against the entire patient population, all of the patient digital twins, and you can go, whoa, you graded a 90. Oh, highly likely you have FSGS. Let me plop it into the medical record and say, here are the 2 approved therapeutics, healthcare worker, right? So they can take it the next step. If it's under 50, you ignore it. If it's between 50 and 90, we can rank order the cost of the test. So you can say, well, you might have it. The next most expensive test would be a urinalysis. That would be what would be recommended. So now you're seeing it as, the 2 of us working together, right? The physician or the healthcare worker and the computer, right? For things. So I'll finish this with, so we had the agent reviewed. I can't explain why I ended up talking to one of the world's experts in FSGS, but we did. I shared it with Howard. I said, Howard, look at this. He looked at it, he goes, this is better than a 4th-year med student. I went, nice. And then I said, well, wait a minute. If you go to med school, how long is the lecture on FSGS? He goes, about an hour. So we euphemistically call this, we're putting Dr. House in the house. Because you look at these, and we're tracking 120 of these right now where orphan therapeutics were built in the past 2 years. You're like, how could a human outside of Dr. House cram all that knowledge into their heads about all of these rare conditions that you can almost barely pronounce? Whereas with computers, this is super simple to go do. So I think that's where it's like, let the computers do what they're really good at, which is a crap load of detail across large volumes of data, and let the humans, no one's ever going to deny there needs to be a human side to this whole thing, but let them do that.
Well, it really keeps clinicians from becoming kind of like keepers of data or data like archaeologists, right? Where they have to, like you said, those incredibly large files, like how can you possibly comb through that and find the information that you need without it being searchable, right?
I think this gets into, the whole AI revolution is going to we're going to end up asking this question a lot, which is if you look at the history of medicine, what is it? It's, I'm going to take all this knowledge, I'm going to pour it in your brain, and I'm going to make you the world's expert on the left side of your right foot. Because all of us want the expert. If I got a problem on the left side of my right foot, I want the world's expert on the left side of the right foot, right? And then I always go, well, why does the guy who's an expert on the left side of your right foot need to talk to the guy who's an expert on the right side of your left hand. He doesn't. And that is the nature of medicine, these super silos that we've created, right? Because there's no way, I mean, given the state of the art of medicine, you can't cram enough stuff in your brain without going, I'm the world's expert in left side of your right foot.
One of my good friends is a emergency room physician, and he talks about how he's been doing it for a little bit of time. And he said that nowadays, whenever he sees like if a patient gets transferred into his hospital, just the volume of data that he has to go through, it's almost to the point where it's like unproductive, right? And he said, back in the day, they would fax over like a 3-page summary. This patient's coming in. I've assessed this. I have a high likelihood of this. Here's what you should do. Blah blah blah. And now it's just like it's just volumes. To your point, just imagine that. I was just thinking about that when you were talking about 3,500 to 7,000 pages. That'd be like if you had like the Lord of the Rings trilogy, but the only thing in that trilogy is just information about one person's medical record, right? And you have to like digest and understand that so you could effectively treat one patient. Just like the overload on that is just, so it's almost like, I think, Gary and I, we have conversations with finance people all the time. We've been talking like there's all this conversation about data. And I think what's becoming clear is the ability to generate data is not the bottleneck. Like the data is not the bottleneck. It's being able to like interpret that data in like a meaningful way that's increasingly becoming the problem we're trying to solve for, not just the solution's in here somewhere, right?
Right.
It's being able to like drill down into what matters and make real decisions off of it, which it seems like what you're kind of solving for.
Yeah, very well said. I think a lot of people, when they hear what we're doing, they think, oh, you're creating data repositories or whatever. And I go, oh, the data, there's plenty of, back to your point, there is plenty of data. I mean, we've done a back of the envelope. The 500 children's hospitals in the cardiology department generate 6 million terabytes of data a year. In the 500, just that gargantuan amounts of data. The challenge problem is how do you compute on it? It's really about computing much more than it's about the data. And I think that's where, and this revolution is occurring around us too. I mean, all of this stuff, Claude, ChatGPT, what it is massive amounts of compute. I mean, your listeners may not know this. ChatGPT 4 was actually trained on 1,000 terabytes of data because it's all text data.
Right.
Yeah. But the amount of compute that went on to train on that 1,000 terabytes is off the Richter scale.
Yeah.
So yeah, it's all about the compute really at the end of the day. How do you want to compute on the data? Not the fact that, and then, how do you get to it? There's plenty of it. This is why I debate with some people. I go, why are you thinking about storing data? There's plenty of it.
Right.
Yeah.
Right.
You don't like this 6 million terabytes? Here's another 6 million.
So I'm interested.
Go ahead, Gary.
Marco.
I was going to say, so like as an educator, right?
Mm-hmm.
And looking at something like this, which I don't know if disruptive is the right word, but this technology, we could just fundamentally change the way that patients and doctors interact. And do you think that or have you had any conversations with healthcare educators? Like, would this fundamentally mean that we have to change the way we train the future of healthcare practitioners? And what does that mean for them?
Yeah, I'll say they're very aware of this and they're very much trying to figure out what it is. How does it change things? But having spent some time in the university system, change is not easy. I mean, just ask yourself a question, which is, why is the curriculum to get a bachelor's degree in chemistry the way it is? That you have to take this class, and this class? Is there some omnipotent force that creates that curriculum? The answer is no, because, I teach chemistry 101 and you want me to change my class? Hell, I've been teaching that class for the past 15 years. What are you talking about? So I actually did this once. I went and looked at the Stanford CS curriculum and went back 15 years. How much has it changed? You may know.
Right.
Now, there's some argument to be made that there are certain fundamental ideas that continue to be fundamental ideas. So why would you change a physics class as an example, right? So there's a certain element of that. But I think all of us are tussling with the question of, if you have kids, what is education going to mean going forward I mean, particularly with the advent of your Claudes, your open AIs, et cetera. What are we trying to, what should we be teaching kids, or extrapolate to what should we be teaching pre-med? Should we be teaching in medical school? I think we're in a heavy evolution of this. And I don't think any of us exactly know. I know they're thinking about it. In fact, I spent time with the dean of nursing up at USF. They're working on it. They're trying to figure out, what does this mean to their nursing population? What are they going to try to teach? So
Well,
they're on it.
yeah, it's also an interesting inflection point, because the capabilities that we have, right, can increase productivity in a way that can also address shortages in certain areas, right, that we're experiencing across the country right now, especially nursing shortages, right?
Yeah.
And it's, how do we leverage technology to address that need, as well as how do we better train people for the future?
I like to think of it as I always realize that the kids I'm teaching at Stanford now were all born after the year 2000. Right.
It's a horrible realization.
Yeah. And a couple of years ago, I used a reference to the movie Aliens, and I looked around the room and it was like, I don't know, it's like Zoom. And no, what did I just say? Aliens?
Yeah, my kids
You
have
guys are a
pulled that
little
on
bit-
us. They were talking about like, oh, things are different when you guys were kids. That was back in the 1900s.
Exactly. You're so last century, Marco. I like the Ripley analogy, right? She puts on this exoskeleton that makes her enormously powerful and is able to throw the mother alien off the ship. I think that's kind of the future model view of the world, is people armed with this technology, right, become super people. And I think that's where we're headed. It's not really, yes, I think we should build what we think of as red, green, yellow applications. But in the end, the transformational power becomes, if we take the best and brightest and make them 10x best and bright. I mean, this is, by the way, kind of starting to happen in software development. Really, the best developers are now X better, is really how to start to think about the AI thing.
Yeah,
Much more than it's a replacement conversation. Of course, there are replacement conversations going on.
right.
But
The
game
conversations
changing.
that we're having, we're finding the companies that are looking at augmentation rather than replacement are finding far more success right now.
Yeah.
And I think the most successful thing, I always talk about, like, one of the most satisfying, like, fundamental feelings in the universe is like feeling understood, right? Like the power to understand and feel understood, I think, is really important. And I think a lot of what you're working with, Tim, is just this transition from knowledge to understanding, right? And the ability is, like, if we can sort of offload a lot of this, like, sort of space that we have in our systems, in our brains or whatever, that is like dedicated to the knowledge, and put this into like a system that is much better equipped to handle the knowledge, that we can really focus on the understanding piece of all of it. And that is really that human to human sort of connection, that if we can increase understanding, whether it be diseases or the way we interact with each other or whatever, I think that's the tremendous leap forward that I think you're bringing to the world.
Well, I think, it allows us to think with bigger scope. I think I was spending a little time with Ronnie Cohen. He's CEO at Sick Kids in Toronto, which has been named the world's best children's hospital. And he talks about they want to build personalized care from data from the zip code to the genetic code. I thought that's such a clever little line, zip code to genetic code. And so I go, because I get what genetic code might mean. So what do you mean by zip code? He goes, well, I'll tell you a story. He said there's a kid who came into the emergency room like every month with an asthma attack. So they'd give him some drugs, send him off, and he'd be back again. After a while, they thought, oh, he's not being compliant. He's not taking his medicine. But they figured out that no, he was. So they started digging further, and they came to realize that he was from a very disadvantaged family, that his living quarters were rat infested. And it was really the reaction to the rat infestation, which is what was happening every month. And they ultimately brought in social service and cleared it up, et cetera. But I think it's an interesting story about how we progressively take more of a complete view of the person, zip code to genetic code.
Yeah.
And now let computers use that digital twin, zip code to genetic code, to begin to either go, hey, this kid there's a high likelihood It has nothing to do with drug compliance. It has
Right.
everything to do with something in his environment. We already know his zip codes in a low income area. I mean, you can imagine that starting to happen where
Yeah.
we and I think thinking of things more holistically at the end of the day is where there's enormous power in this stuff.
So I think what you're doing is awesome. I'm really glad you came on as a guest. If people wanted to get involved, we'll link to the Pediatric Moonshot and in the show notes. What's the best way they can get involved? How can they help? How can they become a part of this?
Yeah, so to your point, pediatricmoonshot.org is website. You can subscribe to the newsletter. We have we have the Pediatric Moonshot podcast on Apple Music and Spotify. There's a whole LinkedIn group around this. So part of the ask is just let more people know and bring more people into the community who are part of the tribe. The thing I always say is it took 40,000 people to get to the moon, the real one. We're a few shy of that number. So bringing more people into the community is fabulous, whether that's, parents, kids, researchers across the board, number one. Number two, we are heavily in fundraising mode. I've been funding all of our work to date. This next step, I talk about completing an AI supercomputer, rough 50 million. And so we've set minimum donation at 250K. We're not trying to go, dollar by dollar. We're trying to do larger sorts of things. We're reaching out to foundations who have expressed interest or have already donated money into children's healthcare. And I think people who are connected into that world or people who are high net worth individuals who find the mission attractive, we're all ears. I mean, reach out LinkedIn to me if you want. Pediatricmoonshot.org has email addresses all over it. We're happy to engage across the board.
Awesome.
Well, Tim, I can assure you that we're certainly going to do our part to get the message out. And we really appreciate you coming on. This has been a fantastic conversation.
Well,
Yeah,
appreciate you guys
amazing.
having me. Yeah.
All
Thanks
right.
again.